Yeah.
But it's so weird.
That's it.
So, it's almost Thanksgiving weekend. Almost. It's almost there. Here's the simple effects graph, simple main effects. You have teach over here, you have achievement here, and you have type of textbook. So at teach 1, are there mean differences? At teach 2, are there mean differences? Then at teach 3 and 4. So each one of those smaller analyses are simple main effect analyses, and that's the same idea as what we had up on the board over there. So the question is, when we look at that, textbook 1 versus textbook 2 at teacher 2, at teacher 3, at teacher 4. So that's what that's communicating. The idea here is, why not just run independent samples t-tests across the means on separate data? Okay, so just a general principle I want to just talk about is, why not just separate the data into teach 1, teach 2, teach 3, teach 4, and run those independent samples t-tests? So, you use a split file approach in SPSS, for instance, and you separate that data, and then you just run those comparisons. Some people would criticize that, and it's not the best way to proceed, and let's think about why. Let's think about why that might not be a good idea. Make sense what I'm asking? So let's just say take teach 1 and just analyze this data by itself. So that would exclude data on 2, 3, 4, and just this data. So if we have, say, a sample of 100, we'd be basing it on what? 25 objects, if it was equal sample size per cell. Criticisms against that. Otherwise, we don't really have to define something called the simple main effect. We can just run univariate t's. Critique. Disagreement on that. Say, I don't know if that's the best idea. Yeah.
It doesn't tell the whole story.
Well, it doesn't, that's right, it doesn't tell the whole story, but we don't want the whole story right here, right? We have our interaction, so now we're like, okay, let's kind of snoop in and let's see where the differences are that are contributing to the interaction, right? That are contributing to the interaction. So when I do this right here, this is the story I want right now because I found an interaction. So, and again, remember that the interaction is between teach and textbook. It's the overall thing going on, right? So it would be wrong to say there's no interaction at teach 4, but there is one at teach 3, because the interaction is the whole thing. But now I'm wanting to split it up and kind of snoop in and see where those differences are. So the question is, am I allowed to just steal this data and observe these mean differences in the t-test and ignore this data? So if I have, I forget what our sample size is, but let's say I have 100 per group, or 100 total, 25 per group, why don't I just take 25 observations out of my data and just do this t-test on those 25, and then go to the next 25 for teach 2 and do that comparison and so on. What's the issue with that? It's just something I want to comment on. Problems with that? Doing individual t-tests like that, yeah.
Is it because it doesn't take, like, I think there's an end problem there somewhere, but is it also because it doesn't take the interaction into account?
Well, yeah, the interaction occurred, right? The interaction occurred, so now, well, you're on the right track if you can expand that. Can you expand?
So, is it kind of the same issue that we had about, no, I can't.
Kind of like the partial eta squared.
Right.
Yeah, I know where you're going with it. It's the idea is this: if I base this on 25 observations, and then I base this on another 25, when I do the overall ANOVA, what am I getting overall here? I'm getting an overall MS error term. Okay, I'm getting an overall MS error term, and the MS error term in my hypothetical example I'm making up on the fly is based on 100 observations. So from the ANOVA, I'm basing my MS error on 100 observations to stay consistent with this example. That estimate, that MS error, what's the purpose of MS error? It's to estimate the overall population error variability. So MS error from the overall ANOVA is our best estimate. It's our best estimate of the overall population variability. It's in MS error. So it doesn't make sense then to take a situation like this and divide that up into smaller portions of data. To divide it up into smaller portions of data and just run univariate t-tests. Okay, why? Because then I'm basing the error term for the t-test on less what? On less
Error.
information, less sample size. I mean, think of it, information is like, we want as much information as we can get to estimate what the error variance is. So usually, what software will do is they'll do that t-test for you, but they're gonna use slightly different denominators, which makes simple main effects a little bit different than actually running those ordinary t-tests. Otherwise, we could just say, let's do simple main effects, and they're actually true t-tests based on independent samples of data. But usually what the software will do will use a holistic error term, which is usually the MS error term coming from the overall ANOVA, because that's still our best estimate of the overall variability. Does that make sense? So a little bit different, and the principle is useful there. The principle in terms of, why are we doing that? Again, it's because that MS error is our best estimate, and that's what we want. So it's kind of like, why base this comparison on less information when we have more? Because if I did just the 25 cases, right, if I just based it on the sample size of 25, what am I gonna get in my denominator? I'm gonna get an MS error if I'm doing ANOVA on the two groups. How good is that MS error gonna be in terms of estimating population variability? Well, not bad, but I can actually do better because I have 100 observations. So more information is giving us that better estimate of that population variability. Yeah.
So simple mean effects aren't inherently inaccurate. You just have to make sure that you're analyzing them in the correct fashion. Is that right?
Yeah, and the thing is you'll see that when in software you know that the software is doing those comparisons, but they're not strictly like the t-tests or the two group comparisons that we've done before. So just recognize that it's usually based on more information. Now, there's times where you might not want to do that, and that's if your variances are wildly different per group, and if you can't assume equal variances per teach group, then you might want to say, you know what, the variances for teach 3 and teach 4 are so weird and so different from the others that maybe I'm actually going to compartmentalize this a little bit and kind of customize my simple main effects so that I'm not incorporating weird variances into the overall error term. But usually when you do the ANOVA, you're also paying attention to variances too, and you're trying to satisfy the variance assumption. Okay, so just be aware of those issues, that those things are not based on individual data, and because you don't want to start doing that. You don't want to start thinking of simple main effects as just saying slice up the data set and just run a whole bunch of tests. Right? Because what happens too when you run a whole bunch of tests, even if you use a global error term, what happens when you run all those tests? With each test is associated what? You're gonna have with each test.
Alpha.
Right, you're gonna have your alpha, you're gonna have your type 1 error rate. So even in the neighborhood of simple main effects, theoretically, we like to say, right, not according to the marketing paradigm that we put on the board, but theoretically, how many simple main effects should you run? Now, how many do you have here? You have 1, 2, 3, 4 for teach, and then you'll have more across text, but how many of these should I run? Well, maybe I should only run a few that are of theoretical interest. Maybe I should plan them in advance and say, well, if an interaction comes out, I may want to compare at teach 3, teach 4. That's gonna be a hard sell because you don't know what the data is gonna look like. So when you actually look at the data and you run the 4 comparisons, what's gonna start to inflate? Your type 1 error rate, right? Your type 1 error rate. What could we do to maybe get a handle on that? It's increasing. You're knowledgeable about type 1 error rates. Say, yeah, but if we do the 4 simple main effects, my type 1 error rate is gonna start rising, right? The family-wise type 1 error rate is starting to get larger. What do you recommend to your lab?
Is there a way you could adjust it like a post hoc?
Sure, you can. You can think of an adjustment like that. Think of like a Bonferroni correction. It doesn't have to be extremely precise. You don't have to, get some computational formula to make sure it's splitting up exactly, as a scientist, how would you treat it? Well, you're testing this one at 0.05, this one at 0.05, this one at 0.05, and this one at 0.05. Well, maybe instead of 0.05, what should you test them at? Maybe 0.01, right? Allow for a little bit of flexibility there. Allow for a little bit of flexibility. And again, that doesn't have to come in the form of a precise prediction, but just allow for a little bit of flexibility so that you say, well, at teach one, I've got a difference, but I'm also running all comparisons. So maybe I'm gonna test it at a little bit more strict significance level. Right? And that's why when you understand the principles at play, you can start to do that a little bit and just be aware of it. So if someone's running a whole bunch of comparisons and they're testing at 0.05 like they're independent, and you've got like 10 comparisons, say, you know what, your type 1 error rate's getting larger and larger, you should probably think about slicing up that alpha a little bit. There's teach 1 versus teach 2 versus teach 3 versus teach 4 at textbook 1. So there's another simple main effect, and at textbook 2. Okay, we're going to skip nested designs. That's just a comment on nested designs here, and take a look at how we'd analyze this in R. So we have achievement as a function of teacher and textbook. Just to make sure this is clear, when we say achievement as a function of, what's that referring to? Well, think of our function statement, just to make sure that's clear. So we've got as a function of teach and text and its achievement. So achievement as a function of teacher and text as a function of. So we look at that, there's our data, which we call achieve 2. And we're gonna identify the teacher and text as factors. So we go fteach, factor teach. And again, what's the purpose of identifying as a factor? Well, that's to make sure it doesn't consider it to be continuous. Because if you just enter these variables and you don't consider it to be a factor, R, SPSS is gonna do it automatically for you, but R may say, oh, I know what teacher is. It's a continuous variable from 1 to 4. And it's gonna try running like a regression on it. It's not gonna be, or it's gonna, what's it gonna try to do? It's gonna try thinking that you have a whole bunch of values in there. So be sure you wanna specify it as a factor. There's our factorial ANOVA. Remember, you could call this fit factorial anything. I just call it fit factorial just for convenience. You could call it ANOVA model, you can call it anything you like, and there it is. So let's look at it. So you got fteach, ftext, fteach by ftext, and also same thing with that fteach. You don't have to call it fteach. You can call it teach f. You can call it anything you want in the identification of a factor. So I'm spelling this out as a factor, but I just did this for convenience. Okay. So just recognize that there's nothing special about fteach like that. So what do we got from that ANOVA? So you're looking at this ANOVA for the first time. You've just run your analysis. Spent a lot of money on the project. It's taken you a long time, and here are the results. Findings? Yep, there's an interaction effect. So, definitely you're looking at all the terms and stuff like that, but definitely this is the one that's going to be the focus, is the interaction effect. That's statistically significant. Your ftext isn't, your fteach is. But as soon as you see that interaction effect, that's the bulk of it. So you're not interpreting your data, you're not going things like this. You're not saying, hey, we have an fteach effect. Well, I'm gonna look at that first, now I'll get to the interaction later. That would be the wrong way of doing it. Always start with the interaction, because that contains the most complete story, okay? So there it is in SPSS as well. Let's get some teach means and textbook means. So there's our cell means. We have a whole bunch of cell means in there. And then we have the interaction effect. So let's just think about what a simple main effect would be here. I mean, you look at it, and it's always good to plot your means out. That's how they're plotted in. You can use this library, FIA, and that gives all your different cell means, 67.33 at the different levels, etc. There they are, they're all there. So you look at that, and maybe you want to look at the data, and it helps you inform which comparison to make. As long as you're not wanting to make too many and fishing the data, what would you like to do? Well, maybe 67.33 versus 74.67 at teach 1. That might be one comparison you want to make, etc. Probably no point comparing these over here. 92.67 to 92.67 because they're the same. Okay. What's the main effect gonna turn out to be for that one? 4, well, I mean, let me just pose this. So at teach 4, I got 92.67 versus 92.67. I don't know if that's statistically significant. I better do the test to make sure. Agree?
0.
Yeah. How many agree? How many disagree? Right. How many not sure? How many not sure of what's going on there? What's going on? Well, you've got a difference of 0, right? You have a difference of 0, so you already know that you're not gonna reject the null hypothesis here. That's regardless of how much of a sample size you have, if the difference is equal to 0, right? Now, if I took this data, if we actually had another decimal point, as soon as you have some difference there, then you know that there's some difference in the numerator, the difference can be, or the statistical significance can be impacted by n. So the magnitude and direction on which the cell means differ. Now this is about cell means in here, and you may want to look at it. So let's look at the plot. Well, it's the same plot as before. There's your interaction effect. Not surprising that it came out to be statistically significant, but here's the question on the final. Is it possible that this has a p-value of 0.1? So there's the graph. Researcher obtains that graph, and the p-value is equal to 0.1. Conclusion, is it possible? Yeah, how is that possible? Yep, underpowered, right? Underpowered. Does everyone get that? It's underpowered. So remember I said at the beginning of class, I said, no, I can stand right next to the graph now. So I got to write this like this. Go, don't be giving your presentation and say, I did some research, no interaction, right? Don't say that, because this thing, you want to go, I didn't find an interaction. There's no interaction in my data. Why would a person say, why would I say that? What's the only explanation? If I say, I didn't find an interaction in my data, right, you don't have enough of a sample size, something's going on, but you do have an interaction in your data. This is an interaction in your data. Okay, this is definitely an interaction in your data. Power issues aside, you may not be able to make an inference to the null, but that is an interaction in your data. Okay, you may not be able to have evidence that it's interaction in the population. That is an interaction. Yes.
Would there ever be a reason why you'd want to do can you do a simple main effect going across? So comparing textbook 1,
absolutely,
teacher 1 and teacher 2?
Yep, that was the one previously that you can also specify that one is, where is it? Right here. Teacher 1 versus teacher 2 versus 3 versus 4. And then how can you follow that up? Well, you can do those more comparisons from there to see which teach groups are different. So there's a number of analyses you can actually follow up with from the interaction point. So again, remember I make the note down here about it's an interaction in the sample data. And that's the same idea as the t-test. Okay, it's actually bolded because it's really important. So same idea as when you're comparing two means. Is the sample mean different? Yes. But what does that say about the population? Where does statistical significance enter in here? What does it mean, say, is statistically significant? So if I said I found an interaction, here's what researchers will say. I found an interaction and it's significant. What does that mean? So again, I found an interaction and it's significant. Do you know what it says on the yogurt package? It says cows treated with BHT. I guess, what's BHT? Some kind of hormone or something? Because they don't want, with cows. Like they're trying to advertise, they're trying to sell yogurt, so they say that cows are not treated with hormones and things. But it says on the yogurt, cows treated with BHT show no significant difference from cows not treated with it. What does that mean? It says that on the yogurt package. It says it. Cows treated with BHT show no significant difference in, I guess, health or whatever compared to cows treated without. And it says exactly that. How do you interpret that as a researcher?
The difference between them is
Let's think about that, right?
likely, so you don't bet them
Oops. Oops, well. Think about it. Why is it going back up there? What's going on?
It's still, it's the same thing.
Oh, is it the same? Okay, sorry, I'm not up with the
I don't know
technology.
why it's doing that.
HT. So let's look here. I guess, no, it doesn't label. I was gonna look for label. It actually says it. Next time you buy yogurt, you'll see it. Yeah, you'll see it. Look on it. So what does it mean? There's no significant difference between cows treated with BHC versus not. How do you interpret that? What could it mean?
The probability of the difference is so likely under the.
How do you interpret statistically? Why is it confusing when you look at that? You say, is that a statistical difference? If it's a statistical difference, why are they mentioning the significance idea? Because if they treated, say, 50 cows with and 50 cows without and did a comparison, what have they found evidence for?
Example.
That there's no difference between cows treated with BHC versus those without. But when they say there's not a significant difference of cows treated with versus without, what are they conflating? Why is it confusing? Because if that's based on a p-value statistic, then that hardly means anything because you don't know how many cows they tested. Right? Does that make sense? When they write that, you're like, I have no idea what this means. None. Right? I think I know what they think it means, and it's probably related to statistics, but I don't think they understand how the statistical significance test works because this doesn't tell us anything. Now, what if it means something else? What else could it mean? Cows treated with versus without show no significant difference. If it's not a p-value idea, what's the only other difference that it could be? Effect size, right? That's what that's personally what I would like to see is, well, there's like, because we know what happens with the significance test. So how about tell us, is there a difference? Is there a clinically meaningful difference of cows treated with versus without? Because that's what we're really interested in, right? But when they say there's no statistical significant, or when they don't say statistical, they say there's no significant difference, you don't know whether they're referring to an effect size measure, or if they just happened to collect 10 cows and 10 cows, tested them, an underpowered study, and therefore found nothing. So we don't know. And even if they said there is a difference, if they said there's a significant difference between cows treated with versus without, what would you want to know? What's your sample size? If your sample size is 5,000, no kidding, there's a statistically significant difference, but then you would automatically say, what's the effect size? Yeah, what's the effect size? It's really, really important. And so that conflation of effect size and statistical significance, it works its way right onto the label where you're not even sure what the statement means because statistical significance is so often looked at and conflated with practical significance, meaningful significance. So as sample size goes to infinity, right, as sample size gets larger and larger, you know you're gonna find an interaction effect. Right, you're going to reject the null for the interaction. Statistical significance is assured so long as there's some interaction in the graph. So long as there's some mean differences happening, you know that it's going to happen. So make sure that that is understood about that difference between the effect size and the p-value. So there's a plot we can produce, and that's a nice plot. It shows your main effects there. We have fteach, and we have text. And there's our text differences, which aren't very big, but then we also have our teach differences there as well. Comparing marbles through AC is something we're not going to do. You can read on that if you want. It's not going to be on the final. More discussion on that in the spring. We can visualize the main effects and interaction effects simultaneously in this plot. You have fteach and ftext, and it shows in the different quadrants what's going on with our interactions. So you can see main effects over here, main effect for teach, main effect for text. We see that text, there's basically no difference. I mean, there's some in the sample. And then we see the interaction effect. There's the one we saw there. But here, it's by textbook. So you have different teach by textbook. So different ways of visualizing the data will inform you scientifically what you'd like to see and what you would like to interpret. And There's a whole bunch of other factors too. Other comparisons that you can make in there, and other packages in R too that you can use. FIA is actually really good though. Here's simple main effects for achievement data, breaking down the interaction effects. So here we have, what do we have here? We have, it does a home test, which is another type of post hoc test. So it's gonna be controlling your type 1 error rate a little bit, and we've got, what, 4 textbooks? So we have, 4 teachers, 1, 2, 3, 4, and at each teach, we're doing a comparison of textbook, And you can change the comparison if you want. You can say, well, instead of F teach for your first statement, you can say F text across F teach over there. You get the comparison again.
Just to kind of tie things in here, for the post hoc, your F statistic doesn't change, right? You're just changing your cutoff value for where.
Okay, yeah, that's a good question. Your F statistic, the question is, does your F statistics change for the post hoc, right? Does your F statistic change for the post hoc? Well, these comparisons are based on an F comparing those two, but what the crucial thing is that the p-value is being adjusted. Now, different post hocs may actually, whether you adjust F or whether you adjust the p-value, different post hocs could present it different ways, okay? So I wouldn't worry too much about saying, well, that F value's gotta be what it's gotta be. The important part is it's changing the error rate a little bit, okay? It's changing the error rate. So when I look at this, you know, and the home test is a little bit different. There's a little few details here on how the home test works. We're not gonna go through it. I don't have enough in here to talk about it, but it's another thing that controls the type 1 error rate. Okay, so often when we're doing analysis, like when you look at this, oh, well, look, the FIA package is offering the home test. Okay, so it's adjusting things a little bit. Might look up some resources, see exactly what it's doing, but we know there's some adjustment on our error rates, okay? Now, you look at this, you know, so suppose this output like appears on the final, and you say, well, you know, what's it adjusting? Well, over here, this is teach 1, and this is a comparison of text 1 and text 2. If you're only comparing 2 textbooks, how could you have an adjustment on the error rate, right? If you're only comparing 2 textbooks, how can you have an adjustment on the error rate? Right? How could that happen? So at teach 1, where's the adjustment? Seems like a little bit of a trick, right? Because you only have 2 means. But where's the adjustment happening here? It's happening across all 4 tests. So instead of testing this comparison at 0.05, you're testing it at a different comparison, a different alpha level. Instead of testing this one at 0.5, you're testing at a different level, okay? So for each comparison, it's not, the correction isn't between those 2 means there. So remember we said if you have a t-test and I want to do a correction on the t-test, no, because I'm just doing one comparison. But this is across the 4 comparisons. This is across the 4 comparisons. And then, let's see, we have interaction contrasts are a little bit different. We're not gonna worry about those. And there's a few summary notes. So there's your chapter 5. I have posted chapter 6 right here, or chapter 8, which I will show right here. Chapter 6 and 7 are on other ANOVA models, which we'll cover in the spring. So we're up to here for linear regression. Okay, so this is linear regression, and we will be developing it next week and talk a little bit about multiple regression as well. So here's the chapter notes. In Montgomery, what chapter is linear regression? It's a little bit later in your book. I think it's like chapter 10 or something like that. I forget just now. That's called fitting regression models, and it involves quite a bit of matrices, which we're gonna spare us until we get to the spring, but we'll have to get into those matrices in the springtime. Okay, we'll talk about regression. Let's talk now about the preview for the final. So I just had Brianna proof this so we know it's good. So there it is, final exam. I don't know why I put it in red. It's not meant to look intimidating. You're gonna print it in black anyways. I think it's just because it's like when the final is, right? You gotta make sure that that's clear. So December 9th, 8 a.m. to 10. Okay, that's what they assign, and it's in the room TBA, which is upstairs. I'm just kidding. It's probably gonna be in this room, but I'm gonna confirm that, okay? I'm gonna confirm the room just to make sure we can get it, et cetera. Final exam consists of multiple choice questions, exact number to be determined, but likely approximately 30 to 40 number. Calculators for the exam are permitted. A 2-page cheat sheet is permitted on which you may include anything you wish. So you can write anything on those 2 pages. You can fill those 2 pages up and you can put anything. So in theory, all material covered in the course is subject to examination, but what's the best way to study? Best way to study is to review all prior assignments. Okay, so all assignments that we've done are, you wanna make sure you know those topics. You wanna look at the midterm exam, thoroughly, make sure that everything's understood there, as well as this worksheet. When working on these questions, dig into any areas in the questions you may not be clear on. So good way to study is looking, for example, for a question that says, what is the difference between doing a contrast versus a post-hoc? Refer to your notes, the book, and helping you explore the question. So questions, yes, wait, do I know what a contrast is? What's a contrast? And you go, I'm fuzzy on what a contrast is. Dig in, get the answer. What is a contrast? Make sure it's clear. Okay. What's a post-hoc? Right? How is a contrast different from a post-hoc, et cetera, et cetera. So even if the question on here asks one question, make sure you're familiar with the environment. And don't be afraid to dig a little bit. Make sure you cover your bases. And that actually serves as good practice for like dissertation defenses and stuff like that. Because you're not only prepared for the question coming at you, you've got what? The legs for the question, right? You've got the legs for the question, which makes you even better prepared. So there's the question, but you know some of the underground to it. So if you're asked this and you know it at this level, a little bit of a deeper level, then this comes across easier because you can recognize it. You can recognize the question, and that's the key. So let's look at just a few. There's the ANOVA table. Okay, so question is, explain the meaning of each term in the table. And the logic of evaluating the null hypothesis for ANOVA by assessing the probability of a K into F. Okay, so you know there's gonna be something on there, and in writing the final, kind of go through the questions and pull something out of there. But do you understand how this table works, the different sources of variation? When we're talking about mean squares, the idea of degrees of freedom, F ratios, all of that. Partition of the sums of squares, eta squared is in there. You see where eta squared is. Refer back to your midterm a little bit. Actually, the midterm didn't talk about eta squared really, but just refer back to your notes on why that partitions, and there's a partition there. Look at number 2, what's the difference between eta squared and F in the ANOVA table? That's what? What is that about, right? Difference between eta squared and F. What is that question about? It's the central, what's the big theme there? Effect size, right? Effect size versus a p-value. P-value is inferential statistic, right? You're getting an F, you're doing an inference on it using the p-value. A little bit different than the effect size. What's the difference? Crucial difference, okay? Crucial difference in effect and p-value. In constructing the F ratio, why does it make sense? Oops, sorry. How do they evaluate different things? How is sample size differentially influential in each? Okay. So, if you'd say, well, gee, I'm not quite sure of that, look back at the notes, get help, talk with somebody about it, and then you unwrap the concepts, you unwrap it. Number 3, conceptually, what does MS within estimate in constructing the F ratio? Why does it make sense to have MS within in the denominator of the statistics serving as the base, serving as the denominator? Well, why does that make sense to do that? We've talked about that in the one way, we've talked about it in the factorial. What's that idea? Without going into the technical details that we talked about a little bit, you have your foot in the door there, right? What's in the base of there? Well, MS within, what's in the numerator? Contains in part the effect you're interested in testing. Right? So that F ratio, that base of MS error, MS within, is serving as that denominator. Why does it make sense that the expectation for the F ratio is approximately equal to 1? Makes sense? Board there. What would be the consequences for the ANOVA if SS total did not partition into SS between and SS within? What would be the consequence? Why would that be a problem if that partition didn't work? What's one thing it'd be a problem for?
It'd be greater than one.
Yeah, it'd be great, yeah, it'd be, yeah, so like, if you take SS total, what if SS total was not guaranteed to partition into SS between plus SS within? What would be the problem with that? What would immediately kind of go out the door? If that wasn't a guarantee for the partition, what kind of becomes a really weird statistic to interpret then? Right, eta squared, right? Eta squared would work, because if we don't know that that's gonna be an exact partition, then comparing SS between to SS total doesn't make sense, because we don't know what the base is, we don't know what that denominator is. If you look at 6, if the null hypothesis were true, what would the expectation of MS between equal to and y? Okay, so there you have to dig a little bit. I said we weren't gonna do much with expectations, but we can do that one. If the null hypothesis were true, what would you expect the expectation of, what would the expectation of MS between equal to? Go back to our factorial notes that we just did. What did we put in there for the AJ? We put in a 0, right? So under that situation, that if it's true, what did that numerator come out to be? It didn't come out to be 0. It justified the use of our denominator, which was what? Exactly. So under that expectation, we have error over error. That justifies that the denominator should be MS error for our test. Justify that the maximum value for eta squared is 1. Why can it not be greater than 1? We've talked about that. Can eta squared be negative? Why or why not? 8, an eta squared value of 0.9999 is large regardless of the research context in which it's computed. Do you agree? Why or why not? Would you say the same thing about eta squared value of 0.8? Why or why not? Okay, something to think about. Eta squared 0.99999 versus 0.8. We've talked about contextualizing our effects. How do you determine whether an effect is large or small? Why is it true that Cohen's d can be greater than 1, unlike eta squared? Is it possible to obtain a result if p is less than 0.05 and eta squared equal to 0? Why or why not? See, and then when you unpack these a little bit, when you talk about them and unpack them, you're really getting your basics on those things, right? You're saying, oh, now I see what the p-value is doing. I know what eta squared is doing. So you can interpret evidence better. Number 11, it's possible to obtain a result of 0.99 and eta squared equal to 1.0. Why or why not? In what sense is omega squared more inferential, et cetera, et cetera. We go down and there's the Levine's test. There's the ANOVA. Some more questions. There's our interaction graph again. Regression output. That's gonna have to wait until we talk about regression next time, but it's right at the end. So what I would suggest is, you can look through that stuff, but study the stuff that we know the most, and there'll be a few questions on the regression. We're not gonna test the regression stuff at anywhere near the depth of the other stuff, because we just don't have, our next class is the last Friday, and then we write on the Monday, right? So we're gonna talk about regression. There's gonna be a little bit, but not very much at all. So I would say, yeah, coming up to the regression stuff, you can go a little bit easier on that. Same thing with your other assignment. The other one was, this one here. We haven't talked about this stuff yet, and we will on our last day. But again, it won't be tested as heavily. So do what you can with these questions for the final. But if these are, if you're having trouble with these, don't worry about it too much. We'll talk when we get back. You first.
Oh, we probably have the same question. So with this assignment, since it's due our next class, do you want us to just try before we learn, or like what would you like
Yeah,
us to do?
for the regression,
Yeah.
I mean, I'm fine with you guys if you want to skip this. That's fine for this. Just because I was hoping we get into regression a little bit, but even once you get into regression, it takes more time. So how about we say, don't worry about the regression stuff for this, do the other stuff. And on the last day, we're gonna do like about half a class of regression. Even that, we're only gonna probably scrape the surface a little bit, so we're gonna go from here a little bit. for the final. So it's not gonna be the last class going, okay, here's regression now, just load this on regression, right? Cause then you have the weekend, right? Like that would be cruel, right? We say, here's regression, I wanna introduce how it works a little bit, we're gonna do it at a very non-technical level, because I want you guys to have a bit of regression, multiple regression, before we go into spring. Spring, we're gonna develop it completely, but it's not gonna be tested extensively on the test.